Welcome everybody. This is Mark Anderson with Staties Incorporated. Today I'm going to be talking about design of experiments for ruggedness testing. Welcome. I look forward to talking with you today, and at the end we'll have some time for a little bit of chat, which will probably be best if you would type in and I'll read it off, and then we can talk a little bit about some of your questions as we go along. So let's get started. So there I am in the lower right-hand corner. I'm speaking to you from Stillwater, Minnesota, which is on the border of Minnesota, Wisconsin. Our office is located in Minneapolis. So I've got you on mute because of the issues of having so many people online and the voice over internet protocol breakups and so forth and so on. But as I say, if you want to put in some chat, go for it. And at the end, I'll go back to it and answer those questions and address the comments. Otherwise, I really suggest that you follow up with questions to me via mark@staties.com, and I'll be happy to follow up later by email. This presentation will be posted to the webinar website at Staties. So to begin with, if you look at your panel, you'll see there's a picture of a hand. If you would press that hand at this point, then I know that I'm getting through and you're with me. Thanks, Ben, Alan, others that would press that hand button, Jennifer, Kenneth. Okay, great. I'm getting a good amount of feedback. Manpreet, thank you everybody for attending, all the way down to William at the bottom. So I'll go ahead and put the hands back down again for now, and we'll continue on with our presentation on ruggedness testing. So the talking points for today's presentation, of course, it focuses on design of experiments and its multi-factor approach that is very useful when you're trying to test field conditions, and it could be a combination of things like wind and rain that cause a failure. This is a very common type of situation that occurs. For example, when hurricanes come through, the sides of the buildings begin to break down and mold will build up. So the combination of things is oftentimes the key for how the systems will maintain themselves in the field conditions. The ASTM E1169 Standard Practice for Conducting Ruggedness Tests provides a really good protocol. It's designed for test methods, which famously break down from the ivory tower development by analytical chemists when they go out into the manufacturing plants. However, I found that it works very well for processes and products to run some type of multi-factor, some type of multi-component testing. And if you do the testing using lower resolution, you can quickly test lots of combinations in a pass-fail type of test, a go-no-go type of test. And one of the designs that works really well for process ruggedness testing, method development, things like that, is a design called a Plackett-Burman. It's not a design that I normally recommend because a lot of people like it for the fact that it offers powers of 4 versus the normal 2-level designs that are powers of 2. However, the Plackett-Burmans tend to be run at the lowest resolution, resolution 3, and people will use them for screening when the main effects are alias with 2-factor interactions. But they're perfect for the ruggedness testing because of the fact that you can saturate these arrays. For example, you can do a 12-run design with 11 factors. It allows you to look at more factors, which is really of critical importance when you're doing ruggedness. So the Plackett-Burmans are going to be featured in this presentation. Now, what's really cool about the low resolution designs that are 2-level, such as Plackett-Burman or standard 2-level, is that you can then fold them over by changing all the signs to the opposites. And that way you can resolve the main effects from the 2-factor interactions. And you can, do some follow-up to figure out what caused a failure in ruggedness. However, hopefully you would get a go on the ruggedness test the ruggedness test would produce effects that are unimportant and possibly also insignificant. And then you would just press ahead and feel assured that your product or your process or your method or whatever the system is will continue to work in the field despite the conditions out there. So that would be the ideal, but we have a path that can go back and remediate, whatever the problems are through the foldover. So let's begin and talk a little bit more about the ruggedness testing methodology. So the ruggedness testing methodology was introduced by Uden and Steiner for analytical methods back in 1975. And the idea that they had was to vary key factors over the ranges that you would expect to be encountered in your normal use of the system. And again, this could be a process product, but they were focusing on test methods. It boils down to a go, no-go type of test. Either it passes or it fails. Of course, ideally, none of the factors will emerge statistically significant, and all potential effects will be unimportant. And we're trying to differentiate between what's significant statistically versus what's important as a practical matter. And really that bottom line is what's important. That's actually the key, more so than the statistical significance. As I said, the Plackett-Burman designs, or PBs as we'll call them, come into play here very strongly because of their simplicity with 2 levels only and their flexibility being multiples of 4 rather than standard powers of 2. They're very efficient for the number of factors that you can put in, which is n-1 if you want to saturate the arrays, so that, for example, the 12-run array can be saturated with 11 factors. And I happen to like the 12-run option. The 12 runs is oftentimes enough to get a decent power, and it allows for plenty of factors. You don't have to saturate it. You could put in 7 or 8 or 9 factors in the 12 runs if you like, by filling out the blanks with what are called dummy factors. They're very convenient to lay out, especially with Design Expert, which is the software that Statis produces. But if you were to do this by hand, which I wouldn't recommend nowadays, it's actually pretty simple. You start with a seed row, and then you rotate these seed rows over and keep rotating all the way down until you finish off at the end with the final row being all minus. So it's actually a very easy procedure to build up these designs. The ones that I've asterisked here at 8 and 16, are equivalent to the 2 to the k minus p standard factorials. So they're a little bit less interesting to run Plackett-Burmans with the 8 or the 16, but they're very interesting to run when you have 12, when you do the 12-run option. I think that fits the sweet spot of a decent number of runs with a decent number of factors that you can do. And it just really is a good place to be for a ruggedness test, in my opinion. There is a story behind Plackett-Burman. I keep hearing more about this. In fact, even earlier this year, I got a little bit more background on this. I can't guarantee that these stories are all true, but from everything I've seen and heard, they were developing these designs during World War II for proximity fuses for anti-aircraft shells. And then more recently, I heard that the British Ministry of Supply kept them secluded in a Scottish castle under guard. Isn't that exciting? And supposedly the data would come to the castle, and then the matrices would come out the other end to the engineers, and then they would go ahead and do their experiments in manufacturing. And the story is that this effort was so secret that it was a ultra secret, and it really developed into an important development for their bomb ordnance and things like that. These Plackett-Burman designs remained classified until after the war, and in 1946, the inventors published the design of optimal multifactorial experiments in Biometrica. So it's really powerful, these Plackett-Burman designs, and we shouldn't overlook them. We should make use of them particularly for the ruggedness testing. So let's move on, and I'll go through some case studies. We'll begin with one that I'm personally familiar with that I call the moisture method mess up. Now, before I move on any further, just to make sure that we're still on track, I'm pressing the button that puts the hands back down. If you're with me so far, please repress that hand button. Okay, William, we're starting from the bottom, going up, Mariana, and all the way up to Alan. Thank you. I do like to check this. If you've heard my presentations before, you know that I need to get some positive reinforcement every once in a while that my audience is still out there, given, the vagaries of the internet. All right, so let's talk about this moisture mess up. So at this time, I was working with General Mills Chemical in research and development, and they had all kinds of fun things going on with their polyamide resin plant down in Kankakee, Illinois, south of Chicago. In fact, one of the things I was just recollecting the other day is they had a bunch of black specks that got into the resin when some burnt parts, fell off the edge of the reactor, and it created a bunch of off-grade. So somebody got the bright idea that they would take that off-grade specked resin and try to slowly work it back into the resin that they were producing, but it was like the cat in the hat. As they went and put back the resin that had the specks in it, more specks were created, and that didn't work. So they were always trying to come up with some kind of a scheme. And it was tricky trying to make this polyamide resin. And one of the key things was they needed to keep the moisture within a certain range, or below a certain level, or it would mess up some of the functional properties of this resin. So after they got through this whole cat in the hat episode with the specks in the resin and they started producing again, well, now wouldn't you know it, the moisture went high, and so they had to throw a bunch of that product off to the warehouse and see if they could do something with it later. So it got so bad that the R&D in Minneapolis was brought in, and the first thing they did is they took a bunch of those retained samples and they brought them back up to the analytical lab. And wouldn't you know it, the results showed that all the moistures were actually in specification. So this really caused the ship to hit the sand, is that the test method itself was biased and producing a high moisture. It was inaccurate. By then, unfortunately, the product had been dumped. So they went back and they decided to run a ruggedness test, an ASTM E1169 type Plackett-Burman experiment on 8 runs. And it was too late, but it was necessary to try to figure out what the quality control had done to the method versus what the analytical test method had called for originally when they transferred it down. So they settled in on these factors that are listed here. The reagent in the plant, because it was so expensive, was recycled. Whereas, of course, in Minneapolis, cost was no object and they always used new reagent. Then there was other factors that they varied, the reaction time from the nominal, heptane, distillation time rate, and things like that. So then they ran the experiment and they developed this half normal plot that showed there was one effect that actually emerged from the ruggedness test. And it's labeled as A, but A is going to be aliased with a series of 2-factor interactions. And the structure of the Plackett-Burmans is such that you get a partial aliasing. And so you have to be a little bit careful when a result comes off like this, and you have to do some follow-up experiments to check it out. And there's a very simple procedure called a foldover that you can use to detect, whether it really is A or one of the interactions that it might be aliased with. And it turned out actually it was A, which is the reagent. And it turned out that when they reused the reagent, there was an azeotrope during the distillation, which means that moisture didn't get distilled out. It got reintroduced into the method. Oops. So that did turn out to be the actual result. It was confirmed. Now, if only they would have run that ruggedness test first. And that's really the take-home message here, is that don't assume that because you've developed something, whether it's a test method or a process or a product, that when you transfer it out with all the instructions laid out, that the people you give it to are going to follow those instructions. Because it's almost always the case that they take it and they say, well, you know, we're going to do things a little bit different. So thank you for this test method. And then they take it and say, those guys up in Minneapolis, they don't really know what it's like out here down south of Chicago. And we've got costs to consider and so forth. So then they start doing things to the method, and they don't tell the people up in Minneapolis, and the people in Minneapolis don't ask them. And there's a problem with communications there. So the communications between the people developing and the people that are accepting these new systems, need to be there. And then let's consider doing a multi-factor test like a Plackett-Burman, and try some things that are going to vary between the development side and the actual field conditions. It's really not that hard. So here's the fold over, and it's, the way that the reagent was pinned down finally as being the actual culprit. So in this case, because if it's an 8-run design, the aliasing is pure. And so the aliasing to begin with was that what we thought was could be A or one of these other two-factor interactions. That's a resolution 3, main effects alias with two-factor interactions. But by doing all the opposites, which is easily done with Design Expert, we were able to see that it was actually A. And you notice between the half normal plot on this slide and the one up above is that there's more squares because more effects can be estimated with the additional 8 runs. And then also the slope of the line is steeper. So it makes the effect of A even more significant because of the power that you get by adding more runs. So that's the story. And as time went along, the communications did improve. I was part of that effort, and we began to form a really good team with the manufacturing between Minneapolis and Kankakee, thanks to some of these failures and learning from that. Okay, so now another example, and this one comes from ASTM E1169, and it's a memory wire, which is a shape-shifting wire that comes back to its original shape, and it's very useful. It's made out of something called nitinol for medical stents, for example. And in this particular case, the experimenter, Simpson, worked through the ASTM standard on this nitinol to make sure that it would translate to the field and continue to operate, as it expected. Now, in this case, when they ran the experiment, it was another 8-run Plackett-Burman. Again, on the 8-run or the 16-run Plackett-Burmans, I'd prefer to go back to the standard 2 to the K minus P structures. They're just a little bit more tried and true, but they're equivalent. Now notice on this half normal plot, it's very interesting because nothing is really standing out. You can basically draw a line through all these effects. So there's nothing significant. However, the other thing to focus on is the range of the effect absolute value. And it turned out that an effect of as big as 13 was not important. And so it being insignificant and unimportant would be one thing. However, if it goes beyond the level that you expect and you think is important, then it would be a fail. So in this case, I take back what I said earlier. They did decide that it was important, and therefore they declared this a fail because of it being too high. And so even though it was insignificant statistically, it was important enough to cause a fail. So then in the old standard E1169, what they would do is completely replicate the design, which is not very smart, because you're much better off if you're going to do a complete replicate to increase the resolution of the design via a fold-over. So I would always recommend a fold-over rather than a complete replicate. Now, when they did the replicate, the power that you got from the replication, which is provided with an indicator by these green triangles, was enough to uncover a series of effects that were affecting this nitinol. And so that led to further work to, determine what it was that was causing it and to see if they could resolve that problem. So the replication doesn't de-alias the design. So at this stage where they see these effects emerging with the added power from replication, they still have the problem of resolution being so low. And so we don't really know at this stage, whether these are main effects or possibly interactions of things. For example, it could be a group of effects that are A, B, and then what we think is F could actually be A, B. And you can come up with all kinds of different families here that would exhibit heredity that could be very plausible. But there's no way to determine that with the replicate. So we really need to think about doing a fold over if you're going to do a further investment. Nowadays, the current E1169 protocol does call for a fold over, not replication, which I'm very happy to see. And I was part of that. I'm a member of the group that developed the current standard. So let's take a little sidetrack at this point and talk about this difference between something that's statistically significant and something that's practically important. And I really like to keep these terms separate, and I've worked on the standard for E1169 to do so. They're really two different things, because from a point of view of ruggedness testing, the most valuable thing to focus on is what is important. And even though something may not be significant, if it's important, then that would be a fail. And of course, if it's important and significant, that would be a very bad fail that, you would have no question needs to be worked on. On the other hand, things that are unimportant and not significant, that's a really good outcome. If it's not important and it is significant, then a little less happiness involved, but probably you could say this is a pass, maybe kind of a provisional pass. Because if something is significantly affecting the response, you may want to dig into that and find out, what it is, even though it's not that important. So think about that a little bit. All right, now I'm going to continue on, and if you're with me so far, once again, since I've been talking for a few minutes here, press that raise hand button. Hopefully this is causing you to think a little bit, this idea of statistical significance versus practical importance. Okay, thanks, Alan. Going down, Ben, et cetera, et cetera. And I do have one question that popped up. And why does the optimization result, George is asking, in box Ben can generate more than 100 results and keep changing after every analysis, therefore getting, that one, George, I think what I would suggest is, since it's not related to the ruggedness testing per se, would you please take that question and send it into the stathelp@staties.com? And I'm going to leave that one off for the moment. So while we're on this slide, I'm just going to write something down here. stathelp@staties.com. And when a question like this comes in that is very specific to a type of design and maybe an actual experience that you've had, send your file. Please send a file, because otherwise all we can tell you is that it depends, because everything depends on the actual data. It's hard to give general answers to some of these questions. Okay, so now let's do one more example, and this is on a pH sensor issue, and we'll see what happens after we do the fold over. So in this case, it's an example that comes from the ASTM E1169 Standard. Results on the first block of 8 runs on 7 factors are showing that the instrument is not rugged to the field conditions. The pH sensor is not rugged. The range is too broad. Remember, that's the bottom part of the axis here. And also, we have significant outcome, as you can see from this half normal plot. Now, the problem with, again, with these designs that are run at very low resolution is that what is labeled as D, for example, could be something else. So all of these things that are labeled B, G, E, and D could be something else and not what we think they are. We're just showing the lowest number of letters when Design Expert labels these. And if there's multiple aliases, it'll just go by alphabetical order. So you have to be very careful to understand the aliasing. And it turned out that actually D was revealed after the foldover to be a two-factor interaction and not D. Now we're still in a quandary because we are still left with aliasing, but aliasing between two-factor interactions, AC, BE, and FG. Now AC is what is being labeled by the program because of it being lowest alphabetical order, but notice that A and C are not main effects that now have been revealed as being true between B, G, and E. And so it makes more sense that this would be BE because that would involve two of the main effects that we have listed here. It turns out that we can then fold over again, but we're going to do what's called a semi-fold, which is only a half fold over. So you start off with 8 runs, you build it up to 16 runs, and then you do a semi-fold and you add 8 more runs, and the total then becomes 24 runs. And when you do that, you de-alias the two-factor interactions. And there's a particular way of doing this. If you can focus on the BE interaction, you can fold over in a way that will de-alias BE and anything else associated with B and E. I would follow up with this posting on the semi-fold to get more details on that. But it's actually quite easy to do using Design Expert. Okay, so the take-homes from this presentation are that the multi-factor tools that you use for design of experiments are going to be very useful for ruggedness testing, where oftentimes the failure is caused by combinations of things and not by one or another alone, but together is what causes the failure. The protocol that's provided by ASTM E1169 Standard Practice for Conducting Ruggedness Testing is very valuable, not only for the methods that it was developed for, but also for process and product development, or any kind of a system. It calls for these low resolution designs by Plackett-Burman, which work very nicely because of them being powers of 2, or multiples of 4 rather than powers of 2. And so there's more flexibility with the Plackett-Burmans. But in particular, I like the 12 run because of it being more powerful. And if you do an 8 run, I'd probably go back to the 2-level design, which would represent 2 to the K minus P. When you run these designs, run them as a go, no-go test. Don't try to infer too much from them, but just as a pass-fail, see what happens and focus on the practical importance. That is the range of response that you see on the bottom on these half-normal plots, which are a very useful tool to assess the results. Significance is really not that vital, at least initially, but of course you would test for that. And then foldovers give you the way out to resolve what causes significant factors in ruggedness, and you can even follow up after a foldover with a further semi-fold to de-alias any two-factor interactions. And these tools are available in Design Expert. So Design Expert makes this really straightforward to set up the initial design, to assess the results of it using the half normal, to then, if you see that there's something important going on, do the fold over, and then if there's two-factor interactions revealed by the fold over, to then do a semi-fold using the design tools and Design Expert. So then to conclude this presentation, and then we'll have plenty of time afterwards for some chat. I highly recommend, if you haven't had a chance yet, to consider training from Staties for the screening and characterization of processes. If that's your goal, then I would recommend the modern DOE for process optimization. And this actually covers not only the screening and characterization, but also, it says in the title, the optimization. So all phases of process development are covered. And this includes detailing of factorial designs, including Plackett-Burman, and then also response surface methods. What's really nice is kind of the silver lining of the pandemic is that we pivoted over to distance learning. And so this opens it up to people all over the world. But just now in the fall, we're going to begin going back to in-person options. So that's something to consider. With the in-person options, you might consider bringing in one of the Staties consultants for a team teach at your location. But the other thing is that you still get the advantage of having a private class, even if it's distance-based. And so the distance learning actually works very nicely for teams where they don't have to travel, and we can, operate out of our homes, like here in Stillwater, Minnesota. So for the process side of it, I recommend the modern DOE class. But if you're working with formulations, if you're some type of a chemist working on paints, foods, pharmaceuticals, cosmetics, whatever it might be, the mixture design class is really awesome. And the tools that Design Expert can provide are really fabulous. So I'd highly recommend that. So consider training, and if you're interested in that, check out our sites on learning about DOE at our main website, and then contact the workshops team, for more information about these classes, a quote, particularly if you're going to do a team teach. All right, that's a little word about the training. Back to the topic at hand, which is DOE for ruggedness testing and making the most from that. I'd like to thank you for hanging on here. I would ask you at this point, if you have any questions, to go ahead and jump in on chat, and let me see if I can address some things for you. So I'm going to go ahead and take a look at the chat, and looking up and down the line to see if there's any questions that come in. Naresh has got a question. If it is important, as we say yes, significant is a good sign, right? I would say what the ideal thing for a ruggedness test would be that it is insignificant, and that it also, though, has a range that's less than what you consider to be important in terms of failing the ruggedness test. So the ideal outcome is insignificant and unimportant. If the range is important, then it is nice if you can also say that it is statistically significant. The key of this is that you power up your initial experiment adequately. If you undersize your ruggedness tests, then you're going to be in a world of hurt, because what will happen is you'll come out with insignificant results, and you might overlook something that's really important. So I would like to say that you should size your experiment using a power calculator, such as Design Expert provides, so that if there is an important difference, you'd have a fairly high probability, more than 80%, of seeing that. And that's why I'm a little bit leery of running these 8-run designs, whether they're standard 2-level or the Plackett-Burman option. And I feel like going to 12 or even 16 runs is much more likely to reveal something that is important, that causes your system to be not rugged when it gets transferred. So that's kind of my background. And beyond that, Let's see. Thank you for the insightful session. You're welcome. Can we have a brief overview of fold over and semi-fold over from the software? Okay, Manpreet, that's a good idea. If you hang on, I'm going to demo that in the software. Sam D is asking for ruggedness. Is there any concerns to have about two-factor interactions? Yes, very much so. I'm very concerned about two-factor interactions. And that's why I want to make sure that I do this multi-factor testing. And ultimately, if I see some things that are failing the test and they're significant, but they appear to be main effects, but they're alias of two-factor interactions, I want to make sure that we reveal that and even go to the semi-fold to get it right down to which two-factor interaction is it that is causing the problem. Is it okay to use two-level full factorial designs for ruggedness testing? Absolutely. I recommend two-level factorial designs. Right, and so the low resolution DOE, Sam D continues his question, because I think what he's thinking is, well, why don't we go with a higher resolution at the very beginning? And the reason is that from an efficiency point of view, if we start with a resolution 3 that's properly sized and it doesn't show anything important and ideally nothing significant, then we're done. Because we're pretty sure going into the ruggedness testing that we've got a good development. That's the premise. So I do recommend going with the low resolution to begin with, but then following this path to resolve it. Now the resolving of it is done very easily with Design Expert. And what I'll do is I'll escape out of the PowerPoint at this point, and I'm going to go back to Design Expert, and I'm going to pull up version 13. And I'm just going to show you briefly some things of how these designs can be set up. So what we would do if we're going to do a ruggedness test is we'd click this new design, and then we would have some options here to consider. We could use a regular two-level design with 8 runs. And what you're going to do is you're going to cut all the way to the right to where you reach the end of the row, and you're going to run this as a resolution 3, which is a red color, with the design saturated with as many factors as you can put in. Now, if you had 6 factors and not 7 with 8 runs, that would be fine. But we're going to go into this red zone that you normally wouldn't do for screening or characterization. Remember that the screening designs are yellow coded and the characterization designs are green. Those are designs that resolve main effects and two-factor interactions. The screening resolves the main effects. The ruggedness tests are not good for screening or characterization, but they work really well for just a go, no-go type of a test. But then beyond the two-level design builder, you can go to the Plackett-Burman option, which is under miscellaneous. And these open up the door to multiples of 4 for the number of runs. So you could do 11 factors in 12 runs. You could do 19 factors in 20 runs and that sort of thing. Now, going back to the 11 factors in 12 runs, you can then, if you don't have 11 factors, at the very end, you just fill out these last factors as dummy factors. And so that's just like a placeholder. So this is one where we fill out the last 3 with dummy factors. And then from there, it's a matter of just putting in the names of your factors, the levels which should be ranged according to what you think is going to happen in the field. And then you can also do a power calculation, which I highly recommend. I'm just going to change these to dummy 1, dummy 2, and dummy 3 because it didn't like me using the same name over and over. And you can see the partial aliasing here, which is problematic with Plackett-Burman's, but even so, they're still effective for a go, no-go type of test, but I certainly wouldn't use them for screening. And this is where the power comes into play. So whatever your response is, you know, the strength of a part that might fail, then you want to put in what's important for you to detect. And let's say a difference of 2, and whatever the standard deviation is, let's say that it's pretty low in this case, then you can see the power coming up here. And in this case, it's quite good with 12 runs, so you're good to go. And then it lays out your randomized plan. Now the foldovers, I can open up a file. Let's go back to the moisture method. And you can see here that the foldover has already been done. And everything has gone opposite. But if we were to go back to the original block, I'll delete out the second block of runs. Then all you have to do is go to Design Tools and Augment. And it already knows automatically, because of it being a two-level design, that you probably want to fold this over. And so all you have to do once you get to this point is press OK. And then all the columns will be changed to the opposite levels according to these green check marks. And then it's completed. And now you've got the second block of runs. And the evaluation of this would show that this is improved in terms of the resolution. And so you can go back and double check the evaluation. At this point now, we've gone from resolution 3 to resolution 4, which means all the main effects are aliased only with 3-factor interactions. And then from there, the next thing you're going to do is augment. And it knows now at this point that you should do a semifold, and there's some instructions on how to do the semifold when you press OK, which I won't get into, but if you follow these instructions, it'll help you figure out what to do to de-alias a particular interaction. So that's just a quick demonstration of how Design Expert makes this really easy. Here again, what I recommend is that you follow up with particular questions like what George had about the box Venkin. And if you're involved with the ruggedness test and you're doing, some work with it, trying to infer what happened, how to follow up with foldover, semi-foldover, contact the stat help at staties.com. And we'll be able to help you. Again, make sure you send your file. Okay, I'm just checking one more time to see if there's any other questions. So I've demonstrated some things. Okay, I think that does it. I appreciate again everybody attending. And to finish off, why don't you press that raise hand button and say goodbye. Thanks everybody. Thanks Mauricio, Norman. Thank you, Andrea, and all. Take care now, and the best of luck. All the best wishes for success moving forward. Bye-bye.